and Tadashi.
Okay, so maybe let's start. So we are very glad to have Bartek Czech from our neighboring country, and we are very glad at least Bartek was able to make it from Tsinghua, and he's going to tell us about holographic entropy inequalities. So over to you, Bartek. Thank you.
Hi, thank you very much. So thank you very much for coming. Thank you for giving me a slot to be here, and also for helping me a lot with the visa process. I was very much assisted by ICTS, and I'm very grateful for it. Yes, so this work is in collaboration with these three gentlemen. Let me just do some advertising. And as this bright undergraduate, I used to be advertising him for graduate admissions, but he's done well for himself, so I don't need to do that anymore. And this talk is about the minimal cut prescription, which we use in the Takayanagi formula. Now, I say minimal and not extremal because basically I will be assuming that we are on a surface of time reversal invariance. So I won't have much to say about the full HRT proposal. But if we do have the luxury of having time reversal invariance, then thanks to Tadashi and his collaborator, we know that computing the entanglement entropy in a holographic CFT can be done in the bulk by finding a minimal surface which covers the right region from the boundary point of view, or it separates a region from its complement. And the minimal cut prescription is so the first thing I want to say is that the minimal cut prescription is, we care about it mostly because of the Takayanagi formula. But if you were contrarian, or maybe if you were a holography skeptic for some reason that I don't understand, then you might also find other motivations for talking about it. For example, if you talk about random tensor network states, without talking about holography, then they too satisfy the minimal cut prescription at large enough bond dimension. And so, for example, you may care about the minimal cut prescription for the following reason. You might want to quantify how random a given quantum state is. Now, a completely random state will be described by Page's theorem. But you could say, maybe I'm interested in one less degree of randomness. I'm going to fix an architecture of a tensor network, but every tensor itself is random. So that's like a smaller degree of randomness. And then the minimal cut prescription would apply. And so you can turn it on its head and say, if you want to detect that a state is not random in the sense that I just described, you just have to find one region for which the entanglement entropy is not given by a minimal cut prescription, and you've done it. And so there are many reasons, also going beyond holography, why you would care about the minimal cut prescription. But certainly the Takayanagi formula is the biggest of those reasons. So I already said it, not all quantum states obey the minimal cut prescription, but the ones that do are an important class of states. And in this talk, I will be talking precisely about those states. So here is a brief review of why the minimal cut prescription tells you something non-trivial about entropies of subregions in a system. So the simplest example is given by this diagram. So suppose that I have a region A and a region B, and I use the minimal cut prescription to compute their entanglement entropies. So there is some surface which computes S of A, there's some surface which computes S of B, and now I'm interested, what is the surface that computes S of A, B together? And immediately I have a choice, or generically I have a choice. I could just recycle the surfaces that did the job for A and B separately, or maybe there is some new surface, which I drew here in pink, and that's another candidate surface. Now, the minimal cut prescription tells me to take the minimum of those two options. So I'm either taking SA plus SB, or I'm taking something else, whichever is smaller. So the outcome is that S of AB is definitely less than or equal to SA plus SB. It can never be greater, because if you wanted to pick something greater, you actually would pick SA plus SB in the minimization. And so this is a holographic proof, in quotation marks, of the subadditivity property of von Neumann entropies. Now, here I gave you a proof. So what is the point of this slide? The first point of this slide is to illustrate that just from starting from the minimal cut prescription, you can derive a lot of facts about entropies. If it holds, then a lot of facts follow. The second thing is that this is not exact. Okay, why did I put the proof in quotation marks? Because there are obviously states which do not satisfy the minimal cut prescription. Here we assumed it. So this is a proof only for that subclass. In this case, we happen to take the minimal cut prescription and derive something which is generally true. But in the remainder of the talk, I will be telling you about facts which can be derived from the minimal cut prescription, which do not hold throughout the Hilbert space, but which are only true because the minimal cut prescription holds. And so the conditions that I will be deriving next, they can be viewed as necessary conditions for a minimal cut prescription to work, or if you ever fail them, then you will have detected that your state is not a holographic state in the sense of satisfying the RT formula. So that's how to understand the things that I will be talking about next. Are there any questions? Oh. So Jaffino raised his hand, and should I be looking
if there's a question online, you can
Yes, yes. Yeah, thanks. Actually, this SAB is that defined as minimum of XA plus SB.
I'm sorry, I didn't actually hear the.
Is SAB defined as minimum of SA plus SB? Is that by definition, or is it calculated to be so?
Oh, you mean here, this option? So here I'm not sure if I understood the question properly because the audibility is not very good, but I think the question was about this. So the reason why, in computing S of AB, we need to take the minimum over all surfaces which separate AB from the complement from the boundary point of view. And SA plus SB is the area of this and this surface, the surface which is the union of the red and the green thing. That's certainly one surface which satisfies those preconditions. So we need to minimize over that as well. I hope that answered the question, although I didn't really hear the question well. Okay, are there any other questions about the setup? Because here I'm just describing what we will be studying. Also, I would like, as much as possible, to encourage the audience to make it a little more interactive. I have to say that it's a little intimidating to see 50 people and nobody saying anything, so please help me and say something occasionally. But okay, so one more thing that I wanted to say, one more motivational slide, is that the inequalities that I will be deriving, there will be inequalities about entropies. Some entropies will be larger than some other entropies because of the minimal cut prescription. I want to say that a modern way of thinking, which hasn't really been fully developed yet, but it's clear that that's the right direction, is to think about this as reflecting properties of holographic error correction. And so why is that true? The first thing to say even here is that the reason why this inequality is true, for instance, this reason, is that if you attempted to violate it, you would first make a phase transition between the red and green surface and the purple surface. Every time you make this kind of phase transition, there is a phase transition in what kinds of errors are correctable, yes? And so the thing that sustains those inequalities, the things that makes them true, is really the same phase transitions that govern our ability to correct erasures on the boundary. And so I think the proper way of thinking about what these inequalities mean eventually is really they tell us some properties about error correcting codes and phase transitions in or limits on some correctability. Now, this perspective hasn't been derived or hasn't been developed fully. So here I'm giving it more as a motivation, both for you and for myself, that I think the right way to think about the subject of this talk is that it tells me something about holographic error correction, but I'm not totally sure what it is. Here in this example, if we talk about a holographic phase transition between in the surface that computes the entanglement entropy of AB, there is the region with a question mark, which is either in terms of holographic error correction, it is protected against erasure of A and B, or it's protected against erasure of C and D. That's exactly the kind of holographic phase transition which makes the inequalities true, and we're very familiar with that picture as telling us about phase transitions and error correction. Okay, question? So perfect is one option. I think that eventually, this is my next slide. Let me start talking about it. I think eventually the perfect understanding of this table that I think we should strive for is that we should be able to look at this table and say, each of these inequalities tells me something about my ability or inability to construct an error correcting code with certain properties. And the properties are in the detail of the inequalities. I think that's this is the perspective that I'm advocating, even though I haven't fully developed it yet. Okay, so I've been talking about, so far the talk has been motivation. I was telling you about why you should care or why you might want to care about deriving relations between, and why it's even true that we can derive relations between entanglement entropies based on the minimal cut prescription. So in this slide, I tell you what has been done so far, at least as of this paper. And the answer is that, well, 5 years ago, we knew these 8 inequalities, really 7, because this is just subadditivity. We knew that. I mean, that's not holographic, and we knew that since the 70s. But other than this one, we knew these additional 7 inequalities. And then, when was it? 2 years ago, a student and I derived another one, so there was an addition of 1. And then suddenly we went from 8 or 9 to 1,800 something a year ago. But this is the state of the art in terms of what you can derive from the minimal cut prescription as of recently. And so I asked you to make this a little more interactive with me. So here I'm going to ask you to take a vote with me. Maybe I can get you to take a stand on this issue. I want to offer you 2 options for how to think about this table. In my opinion, it is either impressive or disappointing. Who thinks that this table is impressive? No one thinks that this table is impressive. That's really bad, okay? No, okay, like 3 or 4 people. Who thinks that this table is disappointing? Okay. And I think that, maybe a few people raised their hands. I certainly raised both of my hands. This table is both impressive and disappointing, in my opinion. It's impressive because it's kind of an amazing feat of human ingenuity that people were able to derive these things at all, on the one hand. On the other hand, I think the goal of all of this exercise was to learn something new about holography. And you stare at this and you say, that's what I learned? That's worse than 42 in Hitchhiker's Guide to the Galaxy. Like, if this is the answer, what was the question? And so the ideal thing...
To be a little more precise, so not only these entropy inequalities, but of course there's absolutely no entropy here. These are geometrical quantities.
These are geometrical quantities, which happen to be...
So there's absolutely no information. This is geometrical.
That's harsh to say. I said, so this is the reason, precisely, so I had the incredible foresight of preparing the slide just for Finn, okay? This one was for you, okay? So here's an example of a set of states which are either random or not random, and you would use those things to decide whether a tensor network state was done with random states or not. That's the kind of thing that you would care about. And I think here you're pushing on the sort of philosophical question. If I derive some physical property of some class of things based on combinatorics alone, am I still doing physics or is it only combinatorics? Well, I think here the interpretation is so strong that I don't like the reductive statement that there is no areas here, but I mean, yeah, you're kind of right, of course. Anyway, here's an example.
The question is whether there's information in the sense of entropy. I didn't mean to say that it was bad.
Why is it? Because the geometry corresponds to entropy.
Yeah.
It's a statement about states which are holographic.
And it's potentially a statement. It's potentially a statement about when areas fail to be entropies. Maybe you can construct a state where you know what the information is, what the entropies are, but the areas are different, and somehow it would relate to these inequalities, and then you would learn something about that failure. So anyway, it's a necessary step in the analysis to understand what's going on.
Would you say that this is a statement of states which have a semi-classical bulk interpretation? Holographic states in large N, those are states which have to obey these inequalities, which all states don't. So it's a characterization of which states have smooth semi-classical duals.
So that was the intention of this box. They're necessary conditions for min-cut to work, and min-cut is what we mean by area equals entropy in the not quantum corrected Ryu-Takayanagi proposal. Then we can talk about what happens when you include quantum corrections. This is a subject for a longer conversation, but It's a conversation for the discussion part, not for right now. So, yeah. So by considering all possible arrangements of minimal surfaces that can ever arise on a common equal time slice of a geometry in any dimension.
You have to admit that it's pretty close to be circular here, right? I mean, you're saying that these are the inequalities that have to be satisfied in order for the min cut to be satisfied, as in some other inequalities to be satisfied. So the inequalities that are
no, there's only one type of inequality. When your statement was involved, I didn't understand what you said, but it was definitely not a description of what's going on.
the min cut, the necessary thing for the min cut.
Yeah, these are the necessary things for the min cut. That's the end. There's no circularity. That's the end. Huh?
But the min cut is itself. I could say that, gee, you're giving me this, and I was like, wow, what does that mean? Let me tell you, they are a really verbose way of stating the min cut condition.
No, because there's they are derived from the min cut condition, but I'm not aware of any way to derive back the min cut condition from it. These are the consequences of the min cut condition, and there are consequences that pertain. So a priori, we have two different quantities. I don't want to spend too much time on it, but I'll spend like a minute or two more on it. A priori, we have two quantities, areas and entropies. And Tadashi proposed that they are the same, but we don't know if they're the same. So a priori. So you give me a state where we know exactly what the entropies are, and then based on these inequalities, without having constructed the geometry, I will be able to tell you there exists no geometry for which areas will correspond to those entropies. That's the way that you would use this. There's certainly no circularity here. We can talk about whether you like the philosophy of this, but it's certainly not circular. So anyway, I'm going to go on, but so here it ended up being a controversial point unexpectedly, just to establish a consensus on whether this table is impressive or disappointing. I think it's both. But anyway, so how to make progress? So some 3 years ago, the first thing to say is that this table has some messy facts. Yes, it's a table of messy facts. And the questions that we already talked through this, are these facts expressed in the table, are they meaningful or are they sort of random? Is there an organizing framework? And does it offer an insight about holography? We kind of said these things, but here are the questions which are the guiding questions for me. And some 2 years ago, Sirwe and I, my student, we thought we clearly need some new insight to make any progress. Otherwise, we'll just be staring at the table and we will go from 300 inequalities to 1,800 inequalities. Maybe next year we can have 10,000 inequalities and we still won't know anything about the actual thing. So, yeah.
Can I just ask if you went up to 6 regions?
Yeah.
Then you would automatically start getting many more, right? So
this is 5. So this is this 8 is the complete set for 5 regions.
Right.
This 1866. A year ago, it was actually 370. This is the most that people have found about 6 regions, but we know that this table is not complete.
Is there an algorithm where a computer for n regions can find all possible inequalities?
There is an unworkable algorithm that in principle could give you all of them, but I mean, it's not something that we could actually run beyond 6 regions. I mean, even at 6 regions, we found these inequalities. I mean, people found them, these people found them, but you can't find all of them. Maybe you can find it in a couple of years, okay? It's a question that with the best computing abilities, it takes a few years to find it, okay, at current technology. So it's a combinatorial problem in some sense, or a geometric problem, which is just not easily solvable.
You'll explain how you find these ones, for instance, these, this is already non-trivial.
I will talk about that towards the end of the talk about how to find them. But right now, I wanted to focus on the structure because the question to me, we could talk about how to find them. I think Matt Hedrick will probably talk about that next week, I'm guessing. But here I want to focus on these questions. And they're kind of, it's not germane to these questions to talk about how to actually find them. So let me not do that now. Yeah. If you have any region with a boundary and you're talking about minimal surfaces for a bulk, anchored on the boundary, then you would still have that. So this doesn't even really assume ADS. It just assumes that there's some minimal. That's evident in the random tensor network perspective. Yes, so I said that this also describes random tensor network states. In that case, there is no talk of ADS or anything like that. Yeah.
That there's also entanglement wedge inclusion. So if you will
That's
A plus B, the SAB might in fact go inside SA plus SB, and then you'd be in trouble. So there's something special about ADS, which is you also have
you're
inclusion.
saying that in flat space you can violate entanglement wedge inclusion?
Or isn't that so? Because you take A and B, and the curve you drew in flat space, that would have more area, right? So you'd have to kind of go by a shorter curve.
No, that's not true. So we can so I want to the short answer is not true, and the discussion about it, let's have it after the talk. Okay, so Sirwe and I thought that we need a simpler question rather than the question about fill the table. We need a simpler question which would have a more direct physical consequence, and we need a question that will have an understandable answer. In some sense, we already have answers to some questions, but we don't even understand what the questions are. So we need a simpler question with an understandable answer. And then what would it mean to make this question simpler? Well, so here the origin of the difficulty is that there are all of these indices, A, B, C, D, E, and you have to keep track of them and their combinations. The proper way of saying this, or a more formal way of saying it, is that we are dealing here with representations of a permutation group on 5 regions, A, B, C, D, E. And the idea is that each of these things generates or transforms in some representation of the permutation group. When we want to look for insight in this table, we're asking ourselves, can I visually just kind of recognize what representations there are and kind of gain insight from that? That's not something that any human will be able to do. And so let's pick out, that's what Sirwe and I thought, let's focus on the simplest representation of S5, the one that we are actually able to understand with human thought and with direct sight. And the way to do it is to just look at every inequality and only keep track of how many regions there are in any given term. This basically means symmetrizing with respect to permutations of region labels. And that means that we are basically focusing on just the trivial representations of the permutation group. So how would that work? Let's take inequality number 5 from this table. I just copied it for you here. And I'm defining a new set of quantities. There will be S with a superscript, which are averages of entropies of regions that have p parties. So SP is the average of all regions and p parties, with p parties in it. Now take this inequality and imagine that you take this inequality and apply every possible permutation on 5 regions to it, yes? Then the SAB and SABC and SABD, you will wipe out by averaging the difference between them. They will all average to the same thing, which is the average of all entropies of free-partite regions. So if you imagine taking every permutation image of this inequality and adding them up, you will necessarily get the same inequality that you started with, but every free-partite region will just be replaced by its average, which is S3 or S2 and S4. And so here I have done that for you. Every free-partite region is replaced by a copy of S3. There are 8 of them. There are really 9 of them on one side and 1 on the other side, so therefore there are 8. There are 6 copies of 2-partite regions, and there are 3 copies of 4-partite regions. So this inequality produces for me this type of simpler inequality, which just involves averages of p-partite regions. Is everyone with me on what has been done on this slide? Please give me a nod if you understand what I just said. Okay, so the key thing is that we can look back at this table and be very intimidated, but if we perform this procedure, then we discover that there's basically just a single inequality there. And I think that tells you that there really is a structure there. And so our job now, this is more interpretive, so now we're more physicists than I don't know, mathematicians. We need to understand why this structure is there. And there was a question, yeah. There is no relation between S3 and S2 in general.
C is equal to SD or? something like that?
These are the only relations, and they take the form of inequalities. So there are no equal sign relations between them. The only equal sign relation between anything is that if you have, if your total system is in a pure state, and you have n regions, then SP is equal to S of n minus P because they are purifiers.
Yeah, that's what I have.
Oh yeah, sure, yes.
Something you can prove this for any n or only for any n up to 5?
As of right now, we have proved it for all n, so this is a known inequality right now. But it was not a known inequality as of a year ago. So I'm telling you about this as a new inequality that we have identified and proved. So we conjectured it 2.5 years ago, and we proved it like a year ago. Yeah. And by the way, because I detected that skepticism, like, are we doing physics? Are we doing combinatorics? So maybe we're just doing combinatorics, but we found a new combinatorial fact that wasn't known to, mathematicians. So that also counts for something. Just wanted to say that, yeah. Nima. Oh, I'll talk about that. That's the next step. Okay, so here's an example. On the previous slide, we found this, and this is actually a special case of that when you set P equals 3. I also said that there is one such inequality that is really a family of inequalities parametrized by P. Put your favorite P, and there's an inequality. So there's a one-to-one correspondence between values of P and the inequalities that we find. And so, yes, so our next task is to try to understand what this means physically. And so to start this, let's make the following observation. There are two ways to saturate this inequality. There are two independent ways to saturate this inequality. One way is to set SP proportional to P, and one is set SP proportional to some quadratic with minus P squared in it. I just set it as P times n minus P. Why did I set it this way? Because of the question that came from there. So I know that those SPs, they have to be equal to Sn minus Ps if I have a pure state on n parties, because complementary regions purify one another. Therefore, whatever quantity I have, it has to be symmetric under an exchange of P with n minus P. So that's how I fit this quadratic. And this quantity should be understood as the minimum of P and n minus P. Maybe I should have written it that way. Okay, so you plug in both of them, and then you realize that both of them saturate these inequalities. And so what we find for now is that there are two independent, separate ways of saturating this inequality. One of them, this one, where SP is proportional to P, is what I would call the perfect tensor entanglement. I didn't make this name. People use this expression routinely. So why is a perfect tensor, why is it called a perfect tensor? Well, maybe, yeah. An equivalent way of saying that we have a perfect tensor is that nothing has mutual information with anything up until you hit more than half of the constituent parties. And this becomes true in here. So let me take mutual information, because I don't have a slide on it, so let me just quickly write it here. Let me take the mutual information of A and B, and suppose that my A is let me call it X and Y, actually, to distinguish it from what's going on here. Suppose that this X secretly has P parties in it, and suppose that this Y secretly has Q parties in it, yes? So XY will be a P plus Q partite state, yes? Now let me take the average of this quantity. If I take the average of this quantity, then this will be equal to SP plus SQ minus SP plus Q. So now if I have this dependence here, you see that this will become 0 if SP is proportional to P. Now, each of those mutual informations is a non-negative quantity. So if the average is 0, therefore all of them are identically 0. And so that's what I mean by saying that nothing has mutual information with anything if you have this dependence.
A holographic state. Right?
Very what?
Very far from a holographic state. It's nothing like
no.
It is not?
It is not, and I'll just like 2 or 3 more slides, and I'll tell you what the holographic state is that does that. So, yeah. But that's really, but the first thing to say is that the happy code has a lot of similarities with that, but I would say this: take a multi-boundary black hole where everything is an identical sort of tentacle, then that's this. Yeah.
Not just for specific choices of regions, right? So you want to take any region in ADS and say this should be true. Or you mean only for some choices of P and P
No,
plus 1?
you give me a state
Yeah.
with an assignment of what I call A, B, C, and D. So we are not playing a game where you give me a state and I say, oh, but in that case, I'm going to choose my A, B, C, and D in that way. That's not what we're doing.
Oh.
What we're saying is that I give you a state with an assignment of what is called A, B, C, and D, and I'm just telling you that no matter how you produce it, you will not be able to violate that inequality. But it's for a fixed assignment of what regions are called what. Yeah. Oh yeah, let me, can I just, I will answer all of these things in 2 or 3 slides. It's impossible to design slides so that I don't, and actually I'm very happy with the questions. That's what just what I wanted. So yeah, that's great, that's great. I'm also, at this rate, I will go through like 1/4 of my slides, but thankfully the organizers gave me another slot in the 3rd week, so I'll finish then. Okay, yeah. Yeah. Yeah, well, through 0, 0, 0, that's true. So we want a non-zero way of. No, because all of the inequalities have the form some number of entropies are greater than some number of entropies. Tensor product state will just put zeros everywhere, so everything will just become 0 greater than or equal to 0. So that question has no. Nima, the answer to your question is a product state will give you 0 greater than or equal to 0. It saturates it trivially. That's the answer. Yeah.
So for the perfect tensor case, are you thinking kind of like a single random tensor?
Yeah, so a single random tensor is really that, and the single random tensor will have these exponentially small corrections governed by Page's theorem. So they're obviously not incorporated. It's the leading term in Page's theorem. Yeah.
And also, if you consider like monogamy or holographic mutual information, does these two classes? It sounds like monogamy and holographic mutual information is not really reproduced by these two classes.
Sorry, maybe there's a problem with my hearing.
Oh, I mean, like, so I think people have shown that there is non-trivial tripartite entanglement in holography, not in like a GHZ.
Yeah, actually, so I want to say that statement about the tripartite entanglement is this inequality with P equals 2. That's a special case of that. That's exactly the thing. Like, I'm trying to tell you that these inequalities are a unifying framework for like lots and lots of things that you have heard before. Yeah. And now we know that they're all part of a single family, which is governed by just a single parameter P. Yeah. Any other questions? So thank you for raising this. Okay. So so we have so this argument here, it demystifies the first part of this slide, which is that this way of saturating this inequality just describes those perfect tensors. Now, there's another way of saturating this inequality, which is this one. And I want to tell you that this describes bipartite entanglement. So how do I understand that this SP having a quadratic dependence on P means that entanglement is bipartite? So this requires an explanation. Here's an explanation. Let's take a tensor network. Oh my God, this is the worst kind of mistake that could happen in terms of the conversion from Mac to Word, to Windows. This is a tensor network, but the tensor network is not showing. So I'm going to give you this argument on the board. Suppose that I have some number of regions, yes, and then the entanglement is entirely bipartite, yes. So the first thing to say about bipartite entanglement is I will just draw some lines, okay? That's bipartite entanglement for you. But there's no reason why you couldn't put lines such that more than one line ends on the same node. Why is that? Well, secretly, there was more than one node here, okay? But then you made some unitary here, which mixed this together so that now those two endpoints of a line became really one endpoint. It's true that you can act with this kind of unitary, but this local unitary didn't change the fact that the entanglement was bipartite, yes? There is still a definite purifier on the other side of this region. So what I'm trying to say here is that a general bipartite entangled state will be such that there will be lines which denote EPR pairs between different nodes, but I don't have a restriction that every line ends sort of uniquely on a given vertex. I can have more than one line ending at a given point, and that's still bipartite. Think of this as there were some EPR pairs, and then at the end of the day, after I prepared that initial state, I just mixed them up with an extra unitary locally. Okay, so the general thing will look like this. There will be just some number of lines in various directions, and I can have multiple lines if I wanted to. Like, why not? Yeah. Yeah, yeah, and because I'm not asking my states to have an equal number, my subregions to have an equal number of degrees of freedom everywhere. Okay, so now suppose that I have n of these things, yes? So I have n regions, and the question is how many different places there are where I could put a line? The answer is that it's n choose 2, yes? If I take, right? So now if I take the total number of lines and divide it by n choose 2, this will give me the average occupation per place where I could put a line, yes? And there is some quantity there. We could compute it for this. I'm going to call it S star, yes? So this is the starting point for my argument. And now the question is, given that I have this bipartite entangled state, what is the dependence of quantity SP on the number of regions P in it? Well, how would you compute the entropy of a p-partite region? You would take p parties over here. You would say that the complement here contains n minus p parties, yes? And then you would ask, how many lines connect p to n minus p? I don't know what it is for this specific choice of p times np, but I know what the answer is on average. Because on average, I have p times n minus p different connections to account for, and on average, each of them comes with S star. And so this is how I conclude that SP is equal to this quantity S star times P times n minus P. Is everyone okay with that? And so this is the reason why bipartite entanglement has this kind of quadratic dependence in its SP. Are there any questions? Yeah. It does. It's the number of lines. I'm just talking about the occupation there. So if there's more than one, yeah, I'm just talking about the average occupation, which could be higher than one. Okay. Okay, so the other thing that you can do here...
Does this state include the GHZ type of entanglement?
No, the GHZ states all violate these inequalities, and they're essentially non-holographic in that way. And we can talk a lot about why that's true, but each one of these inequalities will be violated by GHZ on 4 or more parties.
So like you don't consider this kind of like some inverse isometry, inverse local isometry acting on nodes?
I don't know
what I thought is like consider EPR pairs, and at one point, let's say three pairs, one pair of EPR pairs localized. Can we talk about this afterwards? That's a subject for a longer conversation, but that's not what I mean by a bipartite entangled state. I know what you're saying, but it would take us off road to. Yeah, other people did, but yeah, You can't really do that. You can do something else, which is after you know the 1866, you can ask if you average them, how many of them like land on this for p equals 2 and for p equals 3, and some of them will land on like convex combinations of both p equals 2 and p equals 3. That can also happen. So you can try to do that, and my students have looked at that. I don't have anything sharp to say about that, but you could do it. Okay. So anyway, so far, let's recapitulate. So far, I told you that the messy table, it was messy because it involved a lot of detailed information, which naturally transforms in all irreducible representations of S5 of the permutation group on S5. It's really S6 because you also include the purifier, the 6th purifier in your regions to be permuted. Now, the insight that I'm offering here is, let's just look at the trivial representation. Looking at just the trivial representation simply means averaging every known inequality over the permutation group. And
miraculously, we end with just one type of inequality parameterized by a single number p. That inequality that can't be an accident. That inequality can be saturated. So now we try to turn on more physics, put more physics into the discussion, and we ask, what does it mean to saturate this inequality? And there are two options. One is nothing has mutual information with anything, and we call it the perfect tensor. I reviewed it here. The other one is you can have this quadratic behavior. You plug it in there. It's also saturated. And we understand this as bipartite entanglement. That's the argument on the other side of the board. Okay, so that's this argument. So there are two ways to saturate it. And now we ask, what are the extreme forms of entanglement that are allowed by these inequalities? Now, here the question is, what is a quantum state which saturates as many of these inequalities as possible? Now, as many of these inequalities as possible means saturating all of them but one. If I saturated literally all of them, then the only solution would be all entropies are equal to 0. It would be the product state of Nima's earlier question. That's not very interesting. But so let me saturate all inequalities but one. This is the most extreme form of entanglement, which is only marginally consistent with Takayanagi, but just about to break Takayanagi in every possible direction. Yeah? So these are clearly interesting things. So let's find them. And the answer is, I'm going to describe them through their dependence of SP on P. And obviously we know, or we already know from this, that if I just take a bipartite entangled state that has this quadratic behavior, that's one of them. Another one is that I just can take the perfect tensor, which is this. It goes up to n/2 because of your question and comes down. That's the other option. Are there any other options? The answer is I can saturate all inequalities but one. Suppose that the one that is left not saturated is indexed by a quantity called p prime. There is only one way to do it. You have to go perfect tensor like up to p prime, and you have to go EPR like above p prime. If you haven't seen this result before, then let me just say, because sometimes it's useful, labels can be useful sometimes. I learned from King of the Hill some time ago. Labels can be useful. So I'm going to label this statement as an interesting statement. You go up with no mutual information up to a definite value of p prime. And no mutual information means that there is like no definite purifier for what you have. There is just a soup of information which purifies your state, but there's no way to identify what purifies your state. But you go above p prime, and suddenly everything has a definite purifier. That's what it means to have this bipartite entanglement. And extreme forms of entanglement, things that saturate as many inequalities as possible, are such that there is a sharp transition between those two types of extreme behaviors. Okay. Any questions or comments about that? So, yeah.
You're saying that this middle one is the one which will give you the one that almost, that saturates all but one.
All of them saturate all but one. In this case, p prime is equal to 1. In this way, p prime is equal to n/2. So that's the smallest and the largest value of p prime. And this is the intermediate values of p prime.
Okay, yeah, I see, okay.
Yeah. Okay, so now, is there a question? Oh, yeah, then that's the next slide, thank you. Yeah, so this is already some insight into what it is, but now I want to tell you this statement. This p prime should actually be understood as the age of an evaporating black hole. And so in the next 10 minutes or so, I would like to justify that statement for you. Okay, so here is the recap of the previous slide. And here is a tensor network which just realizes these things. So the way to construct this is the answer to your question. The way to construct a state, and again, my goal here is to justify the assertion that these extreme states that I have, these extreme behaviors that I identified here, are actually stages of evaporation, are precisely what an evaporating black hole passes through in the course of its evaporation. Okay, so the first preliminary here is that if at the level of a tensor network, if I want to describe a state or construct a state which has just these values of SP, the way to do it is to take a perfect tensor that's something that has no mutual information with anything up until you hit more than half of the constituents. So as a tensor network, this is just drawn as a star graph. And then take some number of these legs and then arbitrarily say they will now become one leg. So you just group them together. Not all of them, but just you group some subset of them. And the statement is that depending on how many things you grouped here, you will end up landing on this behavior with different values of p prime. How many you group here determines that value of p prime. That's the statement that I want to make for you. Now, does that sound reasonable? You can check it for yourself. It will take you like half an hour of calculations, and then you will see, yes, indeed, it's true that this is the behavior of this SP if you do that. So now I want to say that this is a tensor network that you have seen like 100 times in your life, because that's the same thing that is drawn when we talk about islands in the context of black hole evaporation. So when we talk about islands in the course of black hole evaporation, I mean, this is a picture that I drew, but I think most of us has seen a picture of this type when we talk about it, which is what? There is an asymptotic boundary. There is a candidate quantum extremal surface. There is the interior of the black hole, and there is the exterior of the black hole. But there is also a bath, which is outside the boundary, sort of. And then these, the Hawking quanta that have escaped from the black hole, they have been captured in the bath. And so they end not sort of in the exterior, not even on the boundary, but in some sense beyond the boundary. Yes? Is that an accurate description of what we do when we talk about islands? If I don't hear a no, then I will assume that you agree with me, and you should agree with me. Okay, Suvrat is not objecting, and he has written a lot of papers about it, so I think that's correct. Okay, so now let's look at this picture, and let's look at this picture, and it is not totally obvious, but you will see that this is actually one and the same picture. So first, there is that reservoir, yes? This is where we have captured the escaping Hawking particles. These are those lines, the endpoints of these lines that have been captured in the bath, yes? Then where do they connect? They connect into the putative interior of the black hole, yes? That's over here. But from the putative interior of the black hole, where else can you go? You can cross the candidate quantum extremal surface into the region which is outside. And if you cross that, and if that happens to be your minimal cut in the minimal cut prescription, then you will pay a certain price for it. The price is the area of this thing. I'm going to designate this to be the area of that thing. If you cross from here, the only place you can go is to that additional region, which is there. And the price you pay is the area of this cut. This is the area of the cut here on this diagram. So to use the same words, I have labeled this diagram over here, and you should recognize that this is one and the same picture, only drawn a little inside out. Shall I give you some time to process this, or is this clear? And so this is these are the states which saturate the inequalities we found. They are the states that naturally occur when we talk about black hole evaporation. I said it in the context of islands because this picture has been popularized when we talk about islands, but it really starts from Don Page, yes? So Don Page, what did he say to us? He said, in the end, the black hole and the radiation are all together in a pure state. So therefore, I draw a Page curve and I say that's how the entanglement, how the entropy of the radiation has to vary with time. It goes up and it goes down. Why does it go up and go down? Because the black hole is initially big, but then it gets smaller and smaller and smaller. And so as it gets, so starting from a black hole which is already, which is old, yes? If I take an old black hole which is already maximally entangled with the rest, now as it gets smaller and smaller and smaller, the entropy has no choice but to go down. And the way that you can, the argument that Page made sort of assumed that the state of the black hole and the radiation together is generic. Generic means random. Random means this star graph, yes? And then the only thing that happens, according to Page, in the process of black hole evaporation is that a subset of the system is designated to be called the black hole, but that subset, as the black hole evaporates away, is getting smaller and smaller and smaller. So this is represented by grouping the components of this perfect tensor, but a smaller and smaller proportion of them. And as I get smaller and smaller proportions of it, I end up landing on just this behavior of this SP. It's in this sense that P prime measures the age of an old black hole. Yeah.
I have a question, and it might be maybe a more natural place to look at the page curve rather than adding this bath and so on, which is just take a black hole, don't have a bath, and then look at different solid angles on the boundaries. So take a region and take it to be small, and then make it larger and larger. So SP would be some region which has solid angle P, SP plus 1 would be solid angle P plus 1. And that, of course, also follows the page curve without a bath, without any evaporation. And what's confusing me is that, because it's clearly it follows the page curve, I think. The entropy kind of goes up till you're at half
I'm
the
not
surface.
convinced. Okay, so is it true that you just get no mutual information for a while until you start this? I'm not sure if you will get a sharp phase transition the same way that you have here.
How could it not be? Because you know when you go fully round, the entropy is 0. And so it must be that the entropy goes, and it's 0 at the beginning.
The question is there any set of regions which have which encompass fewer than half constituents but have non-zero mutual information?
Yes,
that's the question.
It's confusing me, that this statement about mutual information, because it seems to me clear that you just kind of go around the boundary, and it's a thermal state, right? So you keep entropy keeps increasing thermally up to half, and then it decreases.
Yeah, so I don't want to make a commitment to that specific scenario because I haven't thought about it, but let me just emphasize what is special about this thing. It's that we have 0 mutual information until a certain point, and then suddenly we have some non-vanishing mutual information. And what you were describing is kind of the perfect tensor behavior. Now getting that behavior is a lot harder, which is like you have no mutual information up until some number of constituents, and suddenly you have bipartite entanglement beyond that.
What I was describing was really the initial setup page had in mind, right? You take one system, you divide into 2 parts. So you take the full boundary, divide into 2 parts, and so it'll obey the page curve, and SP is proportional to P.
So what's the question, Suvrat?
About why it has no mutual information. Is this a geometric statement that's known that in the black hole background you take two regions and
I think it's the statement of the Hayden-Preskill the Hayden-Preskill statement about black holes being information mirrors. So the idea is that if you start from an old black hole and you throw something in, you can immediately learn it. That means that the whole black hole immediately contains the purifier of whatever you threw in. And that's a statement about this non-vanishing mutual information that we're trying to capture here. So I think Hayden-Preskill is the answer for the question. Okay, so good. So this kind of finishes the first half of what I wanted to say. I'm more than halfway past my time, but I tried to make it accessible and not too quick. So far we have. I told you that all that mess from the beginning can be, it's not entirely captured, but a big part of that is encapsulated by a single type of inequality, and that inequality has a definite motivation in terms of black holes. So I should have said this. You could say, why would we conjecture this? Yes. Well, part of it is that we just stared at the inequality for the table of inequalities for a while, and we found the pattern. But another thing is that we had a physical motivation for it, and the physical motivation was the thing from black holes, and the thinking on our side was this. Whatever it is that is extremal with respect to this holographic entropy cone, with respect to the set of all possible entropies, it has to be some pretty special geometry, which is just about to break in every possible way if you do it. Now, how would you design such a geometry? Is it going to be like a star or a solar system or like the surrounding of my room? That's not likely. It has to be something very special. And whenever we look for something special in gravity, typically the answer is black holes. And so we were just thinking that probably whatever is extremal should be a black hole, and that was part of our conjecture, and indeed it turned out to be true. Yeah, just giving you some sense of what the physical motivation for this was. Okay, so the next question here is how to prove these inequalities, and it took us 2 years of work to start from these inequalities that we had conjectured and get them to the point where, and actually prove them. And so I like to say that, and I'm going, every time I give a talk about it, I say it, and I will say it one more time. It is literally the most difficult thing that I have ever done in my life, physics or otherwise, to prove these inequalities. They look deceptively simple, but the proof is was insanely hard to find, at least for me. Maybe someone smarter would have done it more quickly. And so in fact, the thing that worked was that to prove these inequalities, we ended up inventing a new set of detailed inequalities, going back to the table with the detailed information. Those inequalities would be such that after symmetrization, they would become these inequalities, yes? And we were able to prove these because it was easier to prove them rather than to prove the average statement. And so we had to invent a whole new part of the table that I showed you before, and only then we were able to go back to proving this. Now, well, the thing that we invented is two new infinite families of inequalities, which are described over here. And I do ask you for just a little bit of patience in decoding the notation that goes in there. So it's a little bit of investment. I don't like it when people ask me to go through their notation during their talks, but in this case, it's a small investment that has a big payoff, I think. So please do that with me. So the inequalities assume that I have a pure state which is divided into some number of regions, specifically into m plus n regions. And m of those regions, I call them a1, a2 through am, and the remaining n regions are called b1, b2 through bn. And I assume that m and n are both odd. Okay? And that's a setup that I can imagine. And now I define a consecutive set of a's starting with I denote it with ai sub k, ai superscript k. So you start with I and you take k of them. Same thing for the BJLs. And then there is one last piece of notation which simplifies this. ai plus minus, since m and n were odd, I can take just more than half or just less than half, just fewer than half of those A regions and of those B regions. So plus means just more than half and minus means just fewer than half, yes? So now we know what AI plus minus and BJ plus minus is. It's the consecutively labeled just majority or just minority of regions called A and B. Does that make sense? It's not too hard to decode that notation. So now we go back here, and here is a set of inequalities parameterized by M and N, how many total numbers of regions I have. And here's a new set of, here's another family. I won't talk about it as much, but it's actually even more interesting. But let's focus on this one. So when you look at this inequality, I don't expect that you would have an intuition about it from seeing it for the first time, but here's a word that suggests something. They're toric inequalities. Why are they toric? I have two different summations, yes? And both of those summations go over a cyclically identified set of regions A and B, yes? When I talk about k consecutive regions AI, I mean, I assume that I can go around. Yes, it's the regions kind of are cyclically labeled. Yeah? And so I have summations over two different circles, which maybe motivates the name toric at this level. But I'm going to do better in motivating that. Okay, so at this point, it should be, I assume that it's kind of hard to decode what these inequalities really mean. So here is, to familiarize yourself, here's an example of one of the lower level toric inequalities that we encounter. It just looks like this. Here are those two summations. There's a summation over one and another cyclic direction, both on the left-hand side and on the right-hand side. Okay, so maybe it looks a little bit like a torus, yes? Yeah. Uh-huh. We will do that, yes, you can. Mm-hmm. It is like differential entropy in many ways, and that's, assuming that I would go through all the slides today, I would talk about how this is differential entropy on in the final week. But maybe I won't get there. But yeah, there is a thing like that. Okay, so good. So we have these inequalities, but this is still not so satisfying. So I'm going to give you a better way of describing what these inequalities are like. It's and I should say that when you symmetrize this thing, it becomes that. Okay, so it really does the job for proving the conjecture from before. If we can prove that, we also have proved that. Okay, so here is a better way of thinking about what these inequalities look like. I design a graphical sort of representation where every term on the left-hand side is a face of a tessellation, and every term on the right-hand side, except this extra term, this term is special, but except for this one, everyone is every right-hand side term in the sum is a vertex or a node of a tessellation. And I put together all of those terms and I make a tessellation like that. Because the whole thing is periodically identified, this thing naturally makes up a finite domain out of an infinite lattice, and that finite domain is identified so that it makes a torus. So now we have our first reason to call these things really toric inequalities. Are you with me on what has been done so far? I just represented the terms of the inequality such that left-hand side terms, the bigger than side terms, are faces, and the smaller than side terms are vertices. So far, that's all that's been done. Now let's look at this other collection, this other inequality, the one that I didn't talk about very much. So this, when you do the same exercise for this one, it looks like this. And I want to tell you that there is a reason why we call these projective plane inequalities. So when you do when you design the graph that I just told you about, it looks like this. But then you notice that, let's take the dark blue region. Here it is A2, A3, A4, B1. Here it's A1, B2, B3, B4. These things are just complements of each other. And complementary regions, for a reason that someone pointed out there, have equal entropies, so there's no reason to distinguish them. So complementary regions are actually the same entropy. If you identify them, what you get is that before the identification, you get an infinite strip. After the identification, you get a strip, but this strip doesn't make just an annulus. It makes a Mobius strip because these regions here are arranged upside down relative to these regions. So there's a twist. So you get a Mobius strip from that. And then one more thing to say is that this Mobius strip has a single boundary, which is an S1, but that boundary ends up being populated by all the same entropies. So it's really like one term. So we're effectively gluing a Mobius strip to a disk, and we get the projective plane. And so this inequality, although it's not evident from the way it's written here, turns out to actually have the geometry of the Mobius strip. And now let me just, without going any further, let me ask you, don't you think that there's something in those inequalities that deserves to be studied? Yes, I mean, we would be committing a physicist's sin if we just looked at this and say, oh, we're not gonna study that. No, we have to, yeah. There's really some interesting stuff here. Well, let's go further. I'm going to look at a table that Sergio Cuenca prepared for me 5 years ago. The initial table, which I said was both disappointing and impressive. And here is another inequality that sits there. And then I tried to construct a graph according to the same rules as I did there. And I discovered that it naturally populates. If I try to extend it infinitely the same way that this thing sort of, it's a torus, but it lives on a plane, yes? Let me go to the covering space of what I discover here. It turns out to make this tessellation of the hyperbolic disk. And the fundamental domain of this tessellation looks like this. So if you remember your algebraic topology, you will see that this will make a compact surface, a compact two-dimensional surface, which those surfaces are classified or characterized by their fundamental polygons. In this case, the fundamental polygon is a regular octagon in hyperbolic space. And that octagon, when we identify it the right way, it turns out to produce a surface that has 4 crosscaps. So evidently, this inequality describes the surface with 4 crosscaps, also known as the torus with 2 crosscaps. So interesting. Okay. So far, so there's clearly some relation between two-dimensional surfaces and those inequalities. So I haven't told you one thing, which is key to really understanding what's going on here, although we haven't fully understood what's going on. But a key thing is, I told you so far about what are the, I just said left-hand side terms will be faces, right-hand side will be vertices. But I didn't tell you how to arrange them spatially, and specifically what vertex is incident to what face. That's crucial information to actually construct this graph. And so here's the rule. I'm going to say that a node, so a right-hand side term, is an incident to a face, a left-hand side term, if and only if they do not cross. What does it mean that things cross? It means that they have partial but not complete overlap. And I'm saying that that's not what happens if they are incident to each other. If they're incident to each other, then either they are completely separate from each other or one is inside the other. Does that make sense? And so let's look at a piece of this graph here, and we will see that that's true. Let's take the face a vertex A4, A5, B3. It is inside A4, A5, B3, A1. It's inside A3, A4, B3, A5. It is disjoint from A1, A2, A3, B1. So these are precisely the terms that do not cross this term, and that's why this vertex is incident to that face. So if I tell you, take an inequality, take the left-hand side terms and the right-hand side terms, and see which ones do not cross, they're either contained or disjoint, and make one of them vertices, the other one faces, and try to put a graph according to that rule. There is no guarantee that you will end up with a consistent graph that way. But for these inequalities, we do. And they are interesting graphs. Does that make sense, what we have, how the graphs are constructed so far? Yeah. I don't know if I lost you or not, but since I'm not hearing any questions, I think I should be alarmed by that, but I will just go on. So again, vertex incident to a face, if and only if the two regions are in a nesting relationship with another, either one inside the other or they're disjoint. And by the way, nesting, which Suvrat even asked about before, is very important because nesting is a sufficient condition for the surfaces to not intersect, yes? So the idea is that if you have a region and you have another region, but one is contained inside the other, it cannot be that one is inside the other, but its entanglement wedge sort of juts out, yes? That would be inconsistent with subregion duality, because that would be like saying, I can decode what's going on if I have access to this, but if you give me more access to information, then I no longer can decode it. It can't be that my ability to decode the bulk is smaller because I learned more information. Therefore, nesting has to be a true statement. And the premise for the nesting theorem is this kind of no crossing, yes? So this graph is basically describing all possible applications of entanglement wedge nesting type of reasoning. Okay? Any questions or comments about how the graph is constructed? So far I told you about this graph in terms of faces and vertices, but that's not what graph theorists mean when they say we have a graph. A graph theorist would say a graph is a set of vertices and edges. And you can talk about a face if you can say that there is an embedding of the graph onto a surface, but the embedding is something that happens or doesn't happen. It's not intrinsic to the graph, yes? But here I started from the faces. So from a graph theory point of view, this is upside down. I started from the embedding and not from the actual graph, yes? So you should ask me, what are the edges in this thing? And here is an answer to Nima's earlier question. Edges are conditional mutual informations. And you talked about strong subadditivity. Strong subadditivity is about conditional mutual informations being non-negative. And so so the next statement I want to tell you about is that every edge in this graph is a single instance of a conditional mutual information. It is a trivial fact that if you have a graph embedded on a surface and I have an edge, then how many endpoints does an edge have? 2. How many faces does it have on its two sides? On its two sides, 2, yes? And so there are 2 faces and 2 vertices associated with every edge, correct? Faces were terms on the left-hand side, vertices were terms on the right-hand side. In other words, terms with positive and negative coefficients, if you put everything to one side. So every edge is associated with 2 entropies with plus signs and 2 entropies with minus signs. Let's see what they are. Here is an edge, and I wrote down for you what the entropies are. I just copied this plus this, minus that, okay? It doesn't look like a conditional mutual information of anything yet, but remember that these entropies are, we're working in a context of a pure state, so I can always trade any of these regions for a purifier. When I trade them for a purifier, then this quantity, which describes this edge, becomes this. And let me ask you, does this look like a conditional mutual information? It is a conditional mutual information of A3 and B1 conditioned on A1, A2, B2. That's what it is. And so this edge, at least, is associated with a conditional mutual information. In fact, every edge is associated with a conditional mutual information in this graph. So when I give you the graph, I'm basically giving you a collection of conditional mutual informations. Now you could say, isn't that trivial? Conditional mutual informations are already non-negative. So these inequalities don't tell me anything. Aha. But the tessellation only tells me about this and that. It doesn't tell me anything about this. There's a single term here which is not captured by the tessellation. And so the tessellation tells me that there is a certain combination of conditional mutual informations. I already know because of strong subadditivity that's greater than or equal to 0, but these inequalities improve on it. They say it's not just greater than or equal to 0, it's greater than or equal to this single global term. And that's the improvement that the toric inequalities are giving you. So it's a collective improvement, it's an improvement on a collection of conditional mutual informations. Any questions about that? So this answers your question from 15 minutes ago, Nima. Any questions about that statement? Okay. So, so in the remainder of this talk, yeah.
Do you have any intuition about this sum of conditional mutual information is larger than this entropy?
Yeah, so that's what I want to, yeah, so I will talk about that in my next talk 2 weeks from now. I will talk about it a little bit in the remaining 13 minutes and 40 seconds. Yeah. Yeah.
Where you keep one of the sides fixed and just alternate the other guys. And this setup looks like adding the area of non-overlapping triangles involved.
Good. Yeah. So maybe let me make this comment right now. So, one thing you can ask about. Yes. So let's take a step back. I mean, I just have 13 minutes, so I'm not going to go through any detailed stuff in the remainder. Let's just kind of make it into a discussion from now on. So, so I'm going to elaborate on what you said, Nima, just now, which is that let's go back and ask the question: why was it true at all that these inequalities were related to two-dimensional surfaces? And for example, you could say, is it likely that there will be some other inequalities that are related to three-dimensional like manifolds? Yes. The answer, in my opinion, is no. So let me tell you about why I think two-dimensional manifolds are special and why they show up here. So it's really on this slide. The statement is that every edge here, every edge kind of is associated with a little piece of area here, if you like. Yes. And every edge here is associated with a conditional mutual information. A fact of life is that the conditional mutual information has the same transformation properties as a two-form. So if you think about that, so it's actually right here, yes? Imagine that you were to construct a two-form, yes? Then a two-form is naturally associated with a little parallelogram where you say, take one corner and the opposite corner with plus sides and the other two corners with negative sides. That's how you make a discretization of a second partial derivative, yes, which is what a two-form is. Are you with me on that? Plus, plus, minus, minus. Well, look at that, plus, plus, minus, minus. So this is your reason for why every edge is associated with a conditional mutual information. It's also associated with a two-form, yes. The moment you realize that the conditional mutual information naturally has a structure of a two-form, and I have made a lot of use of that factoid in my prior work when my friends and I worked on differential entropy and kinematic space. Kinematic space was really a geometrization of conditional mutual information into a manifold, which we called kinematic space. So here, we can also say that this torus and the other things are also kinematic spaces, in the sense that the natural two-form that lives on them is comes from a conditional mutual information. But in this case, we constructed this kinematic space, a space with a two-form associated with a conditional mutual information, we constructed it such that it became a compact manifold. And on a compact manifold, a lot of new interesting things happen. In this case, what happens is that you get a new topological quantity, and that topological quantity is bounded from above by these conditional mutual informations. So yeah, that's what I think the reason is why two-dimensional surfaces are naturally associated with these inequalities, because of the two-form conditional mutual information relationship. Any other questions or comments? Yeah.
Can I say that this set of inequalities is very roughly, it's containing a lot of information of conditional mutual informations. And on top of that, there's this extra piece on which SA1M. Which
yeah,
you said,
it's just this notation. Don't worry about this notation. It's just A1, A2. It's all the A's. It's all the A's. Yeah.
Yeah. So I thought you were saying that this is not covered in the tessellation. So this,
Yeah, it's not. It's never. So yeah. So the statement is that everything that lives on the torus makes up a combination of conditional mutual informations is greater than or equal to the stuff that doesn't live on a torus that's a single term. So the torus quantity bounced from above another quantity, or really the other quantity not on the torus bounced from below the conditional mutual informations that live on the torus. That's the way to think about it. Okay. And so the projective plane inequalities have the same structure, but now the conditional mutual informations make up a surface which happens to be a projective plane topologically. Okay, so so let me just sketch for you I have too many slides for the remainder, but let me just briefly sketch for you what happens like if you look deeper into the structure there. So the next thing I wanted to tell you about is that the toric or the toroidal structure of this new kinematic space of these graphs that we have constructed, or the projective plane structure, it's not just something that happens to be true or happens to be useful visually or something. It is the real reason why these inequalities are true. They're really true for essentially topological reason. So going back to my motivation, I said, ideally, I would like to say that each of those inequalities has an interpretation in terms of error correcting properties of the bulk, that in my ideal, like forward looking sort of aspiration, I would like to say that each of them should be interpretable in a statement in the form, a holographic code with some properties doesn't exist, or it exists, and moreover, it can also protect against additional errors. This is the kind of statement I would like to be able to make. I can't really say that about the inequalities at present, but I'm working towards it. But whatever this statement is, it will be a statement which is topological in character. That's what I want to tell you about next. So, so now I'm going to answer Suvrat's question from like the first 5 minutes of the talk, which is how do you even prove the inequalities? I will very briefly sketch for you how those inequalities are proven, and then I'll tell you about how the general inequalities are proven. Then I'll tell you about how specifically these inequalities are proven, and then you'll see that without topology, you would have no choice you would have no hope of ever proving them. They're only true for topological reasons. So first, the general framework. The general framework is that you make a table which has all possible assignments of zeros and ones to the left-hand side terms of the inequality. So for example, here we can take monogamy of mutual information. That's this. And then for every term on the left-hand side, I make a column in a table, and I assign all possible zeros and ones here. I have 8 things here, yes? And then I fill the table with assignments of zeros and ones to the right-hand side terms. But here I don't have to go through all possible zeros and ones. I find a special assignment. And I need to construct this table such that 2 conditions hold. First, if I take any 2 bit strings from the left-hand side, their difference means just counting how many places they're different. Their difference on the left-hand side is greater than the difference on the right-hand side. That's the reason. That's the first condition to satisfy, and that's called the contraction condition. The second thing is that every region indicator must map to a region indicator. What does that mean? Here we have regions A, B, and C. Let's look at the region A. A region A is contained in the term AB, so I'm going to put a 1 here. It's not contained in BC, so I put a 0 here. It is contained in AC, so I put a 1 here. This is the reason why this row is called A, because 1, 0, 1 expresses the fact that A is not, and is in these terms, yes? And then I do the same thing on the right-hand side terms. A is contained here, not, but here it is, 1, 0, 0, 1. And so these things, the rows that correspond to the regions in question, they have to map to each other. Indicator has to map to an indicator. If I construct a table, yeah, so I will explain this in the next two graphs. So first, this is the technicality. I need to find a table which has these properties, that it's a contraction, that's this property, and that indicator goes to indicator. So now let's understand why that's true. I'm going to take the even simpler example of subadditivity and prove it that way. So the proof of subadditivity, which I did in the first slides, in this form would take the form of this table. And let's try to understand what that means. The 0, 0, and 0, 1, and 1, 0, and 1, 1 correspond to these regions in the bulk. They are regions that are, respectively, are not contained in the entanglement wedges for AB and for BC. You see, this 1, 0 means that I'm inside the AB, but outside the BC entanglement wedge, yes? Does it make sense that every assignment here corresponds to one region in the bulk? So far, so good? Yeah. And now, what is the meaning of the things that we are looking for in this table? Well, we're trying to find a set of candidate RT surfaces for the right-hand side. And the way we're going to do that is that I'm going to take the union over all of these regions which have a 1 in that in this column, and take the union of all ones. That's going to be my candidate RT surface for, in this case, for B. So you see here in the B column, there's a single 1. So I'm only taking this term. Does that make sense? And this is my candidate. In the ABC column, I have 3 ones, yes? The 3 ones contain 0, 1, 1, 0, and 1, 1. So I'm going to take these 3 things, yes? So let me take Suvrat as a test case. Does it make sense how those ones construct candidate RT surface? They're not actual RT surfaces, they're just candidate RT surfaces. So the 1 here means that I'm going to take just the region for which this 1 was assigned. That's the 1, 1 region, that's this region. Yeah. Uh-huh.
So for instance, we have AB plus SBC is smaller than equal to twice of SABC.
Sorry. Where is that?
I'm just reading it up.
No. You're not reading any inequalities from the table. The table is just a way of finding some RT surfaces, but they're not even real RT surfaces. They're just candidate RT surfaces. And then the minimization will make something which is even smaller on the right-hand side. So here, so to prove the inequality, I just have to tell you that if you give me a surface for AB and BC, then there is definitely some surface that covers B and it covers ABC, which has smaller than or equal area. But that surface I'm giving you doesn't have to be minimal, because the true minimum will have an even smaller thing, so the inequality will be even more true. So I just have to find something which has equal or smaller area. And this table tells me how to do it. So the contraction condition, going back here, is the condition that after you find these candidate surfaces, then they really do have a smaller area than the starting left-hand side terms. Whereas the indicator going to indicator condition ensures the homology condition for the terms that you are constructing. And so this is the rationale for why we're looking for that. You mean the inequalities? The inequalities are definitely true. Yeah.
No, I know this inequality is true. There are other inequalities I might be able to read off from such tables.
Oh yeah, if you give me a table which works for that inequality, then that inequality is proven. Yeah, that's it. That's all it takes to prove a given inequality, which may or may not be true. But you give me an inequality.
But there's this additional condition, right? That I have to somehow make sure that the right-hand side I minimize somehow. And
after you you found something which had equal or smaller area. And now you say, oh, let me minimize further. That's not going to make this statement false. It can make the statement even more true in some sense. Yeah. Okay, so this is how we find these things. And here's an explanation for why that's true, which we don't have time for. So now let's go back to these inequalities and say, how would you prove them by this method? Yeah.
So SAB plus SBC is also greater than or equal to twice SB from this table, right?
So why is the, sorry, are you
SAB
reading?
plus SBC is also greater than or equal to 2 times SB.
Is that the true statement?
I don't know, but it's true in this table.
No, this table is not saying that at all.
Why? I mean, I didn't understand. It is, right? In this table, it's true that for any assignment, SAB plus SBC is greater than or equal to twice SB.
Oh, no, again, I'm saying the table is not telling you about what is bigger than, this table only pertains to this statement. It doesn't pertain to any other statements.
I didn't understand. Why is that? I could make a different table with A, B, B, C, and only B, and throw away the A, B, C. And then I would have this assignment.
But only B, but a single B.
A single B.
Yeah.
And then I can't have any other assignments other than this, the ones you have, just by. And then there's an inequality, which I suppose is SAB plus SBC is greater than or equal to twice SB. I don't.
Well, then I would have to make another row like this with B here.
Yeah.
Yeah. But if I make that,
why isn't it enough to have only one column?
Because I have 2 of them, so then I would have to make a you want me to put a coefficient of 2 here.
Yeah.
Well, that coefficient has to find the reflection in the table, so I would have to find another to make another column.
Then I have to put identical bits for that one, right? That's B.
Not necessarily. On the right-hand side, you don't. And the reason why you don't is that you're just looking for candidate surfaces. So the candidate surfaces don't have to be real surfaces. So you can make a different candidate for one copy of SB, a different candidate for another copy of SB. The minimization will then make them the same. But at the level of producing candidates, you don't have to. But anyway, the inequality you're talking about is false, so it wouldn't have worked. But we can talk about that afterwards. So I already got the ringer, so I have to stop in a moment. But let me just say what the so imagine trying to find a table like this one or like this one, but for inequalities that have these arbitrarily large numbers of terms. Yes, that's a pretty daunting task. And so we looked at some brute force assignments of 0s and 1s. And at some point in the game, we looked at an intimidating set of tables of this type. And the reason why I say that proving these inequalities is the hardest thing that I've ever done in my life is that basically my students and I stared at this long enough and we understood how the 0s and 1s were selected. So imagine doing that. And let me tell you about how it really is done, which is that here's some rule that makes it work. We are supposed to start from some 0s and 1s assigned to the faces. Remember, these were the left part of the table. And we're supposed to find some 0s and 1s assigned to the right part of the table, which are the vertices. So the schema for the problem that we are solving is that you have some 0s and 1s on the faces, and you have to decide whether the vertices here have 0s and 1s. How do we decide that? Every time you have a 0, you put lines like this. Every time you put a 1, you put lines like that. And it creates a new graph for you that looks like this. And then the rule for assigning 0s and 1s is this. If you are surrounded by a contractible loop, put a 1. If you are not surrounded by a contractible loop, put a 0. If you are surrounded by a contractible loop, but there is more than one vertex surrounded by the same contractible loop, then choose 1, and that 1 has to be chosen according to some definite way. For example, bottom rightmost vertex in that thing. So when I follow this, I end up with this assignment of 0s and 1s. Believe it or not, what we saw on this slide is describing this rule. And I would like some of you, I think for like 80% of you, you're thinking like, okay, here's another thing and I want to go have lunch. But maybe 20% of you, or maybe 10, or maybe just one person got actually interested and intrigued by this thing and come talk to me, because this thing is deeply physical. it's actually telling you these loops here that I'm talking about here are not just something that we made up because it worked, but they express necessary and to some extent sufficient conditions for what those candidate RT surfaces have to do in order to not violate entanglement wedge nesting. So these topological things, these loops, which are either contractible or not contractible on the torus, they're really telling you about certain RT surfaces being consistent with entanglement wedge nesting, and the consistency is driven by topological considerations. So that's really what I wanted to tell you, that those inequalities are really true because of the topology. And there's way more to say about how topology interplays with entanglement wedge nesting. And so I'm going to, this is the detail of that argument. It's very topological. You can see loops doing various things, and they're all about this entanglement wedge nesting. But I'm going to stop here. My title was flamboyant, everything, everywhere, all at once, and lots of things. So here's just a justification for why I made my title the way I did. I believe, talked about all of these things, except this one and this one. And this one I'm leaving for myself for 2 weeks from now. So thank you very much. But I made it so interactive that I think we don't, so Nima has a question, but maybe we can just talk collectively at lunch after Nima's question. Yeah. Uh-huh. Yeah. Uh-huh. Mm-hmm. Yeah, and we can talk, yes, I have some more detailed statements about that, but at the level of this public conversation, the answer is just yes. Sorry, there exist no new inequalities that we found. Well, the projective plane inequalities has they have a single term which has a different coefficient from all the rest. And that's the term that makes a cap that closes off a Mobius strip into the projective plane.
So this, you have this sum of the conditional mutual informations, and then there's this extra entropy term on the other side.
Yeah.
And those conditional mutual informations were basically giving you this graph on this surface.
Yeah.
Is there some topological understanding of this other entropy term?
Yeah, that's really the thing that I don't have time to talk about. But there isn't like a super quick answer to this, but let me give you sketch the answer briefly. So at this level of the diagram, yes, like remember I said to find this contraction map, we have to go through this procedure where zeros and ones on faces produce these loops, and then I make zeros and ones, and yeah, okay. So now it turns out, suppose that you change one of these bits from 0 to 1. What happens to the loops? Generically, what happens to the loops, like let's say that you change this 0 to a 1. The rule is that 0 means horizontal lines, 1 means vertical lines. So what's going to happen? This loop and this loop, they will join up. Do you see that? Yeah, okay. So generically, what happens is that flipping a thing here means that two loops here will join, or you could do it the other way around so you can break them, yes? But in any case, the number of loops here should change, yes? So that means you change this by 1, and the number of loops here also changes by 1. That means that the sum of zeros and ones here plus the number of loops here, modulo 2, should always be constant. That's wrong. It turns out that very non-generically, occasionally, it is possible to change the 0 and a 1, but the loop transforms itself without joining with another. And that can only happen under some very special circumstances. So the normal circumstance is that you have these 4 endpoints of a loop, and they do something, yes? And the generic thing that we have over here is that, for example, I have it like this, yes? These are my loops, yes? So now, that's my starting point. If I now break it and do this, then I have joined 2 loops into 1 loop. That's the generic circumstance. Now, what is the non-generic circumstance? The non-generic circumstance is that maybe this thing connects like this, And in that case, there is actually a single loop, and the single loop goes into a single loop. You can see from this picture, I'm not sure if you can see it from this picture, but this can only happen on the torus, it cannot happen on the plane. Okay, so very occasionally, a flip here will cause not two loops to join into one or vice versa, but it will rearrange a single loop. If that happens, the quantity we talked about before, which is the sum of zeros and ones here, plus the number of edges, loops here, will actually switch from 0 to 1 mod 2. That quantity is a topological characterization of an assignment of these zeros and ones. And that quantity controls what to put for the bit for this final thing, and that's how we assemble those RT surfaces. And so really that term is entirely determined by whether or not the number of loops here equals or does not equal the sum of these things mod 2. That's your topological thing. Now imagine that you, sorry, I'll say one more thing. Imagine that you had a two-sided black hole where the A regions live on one side and the B regions live on the other side. The bit that I just described for you controls how to collect, how to make up a candidate RT surface for all the A regions. That's a candidate RT surface for the entropy of a single side of this two-sided black hole. And I'm just telling you that there's a topological index that controls how to make it. So really the entropy of a two-sided black hole is topological in that sense. Yeah.
Are these inequality, coming back to gravity and ADS, are they true for all states beyond the vacuum in ADS?
They're true as long as we can equate entropes and areas, going back to Finn's correct objection.
So there is if you do HRT surfaces for general states, these
there are two directions in which we can attack this statement. One is if I include time dependence and go from RT to HRT. Now it's extremal and not minimal surfaces. Does it still work or not? Matt Hedrick has been championing a long sustained effort to show that this is true. The status of that statement is uncertain, but I think it's virtually, everybody who thought about it believes that it's true, but it hasn't been proven. And I can tell you more about the detailed status of that, of trying to prove that. The other direction is, what if I include quantum corrections? Now, quantum correction, that's the more...
Sorry to interrupt you, because I wanted to ask about that. Before quantum, can you do alpha prime correction?
Oh, alpha prime correction.
Because that's better controlled. I don't know. Suppose we want to do alpha prime. Is there a way to test?
Oh, I haven't thought about this at all. But for alpha prime corrections, but sorry, we know how to, do we know how to quantify? Huh? Oh, you mean the... I see. That's the, that part is, yeah, so anything walled-like is fine because because here I just said we need to minimize some quantity, which is local on a codimension 1 locus, yes? And so the walled entropy satisfies that, that condition. So area doesn't have to be area, it could be a generalized area that it's just some functional on a codimension 1 locus that separates a region from another region. The codimension 1 is key though, so going to onto quantum corrections. For the quantum corrected RT formula, it has the bulk term. The bulk term doesn't localize on a codimension 1 object, so then it fails. And there is a question about whether the inequalities are useful for anything after quantum corrections are taken into account. This is a subject for another long conversation and something that I really would like to, I'm trying to understand in detail. Here again, my strong belief is yes, for various reasons. But one reason is something that I like to call the unreasonable effectiveness of the RT proposal. So what do I mean by that? Maybe I think everybody would say yes to the following, would agree with the following statement. The most impressive thing we have learned from the quantum corrected, from the quantum extremal surface prescription is the ability to compute the page curve according to some rules. I said everybody, maybe Suvrat would not agree, but like most people would agree that that's the statement. But then we're back to this picture, and then you realize, oh, this is supposed to be the biggest triumph of the quantum error-corrected formula, but I was able to talk entirely about geometric quantities and cutting RT surfaces, and I was able to recover all the same features of it. So the things that would really like not be geometrizable were not employed at all in this argument. So I do posit a question for myself and for everybody here. Can we learn something from the quantum extremal surface formula, which is interesting and surprising, but in a way which is intrinsically not geometrizable? Like this is geometrizable because according to the sort of ER equals EPR prescription, every time this Hawking particle was absorbed by the bath, I was able to think of this as a very narrow and long wormhole. Yes, that's geometric. And that was okay. Now, is there any, but I know that I can do it for any quantum state. I can do it for GHZ type states. Yes, there's no description of that type for them. So can we learn anything about gravity from quantum extremal surfaces that would really rely on this sort of GHZ-ness, which has where the entanglement is intrinsically not geometrizable? I know of precisely 0 examples where that happens. So I have a strong belief that this is what I call unreasonable effectiveness of the geometric description. It even works when we're trying to capture bulk entanglement.
I have a couple of questions. First, in the case of the page curve, of course, you can geometrize it in these W holographic models. And second, I think this kind of generic page curve is, basically about the same as looking at the page curve as a function of angle, without having evaporation. So I don't think black hole evaporation is key to the page curve. It's just the fact, you just take a region and just increase the size of the region. We can discuss it later. It's a question I asked. But just to have a different question, this is just.
I just want to say, maybe this slide is actually my expression of agreeing with you, because I'm saying you didn't have to go through all of these things. You could have just studied these these like properties of.
Yeah, and in fact, you can just increase the size of that black region, and you'll get something. This
exactly.
Be,
That's exactly what I'm saying.
Yeah. The question I have though is this interesting comment you made about string corrections. So let's say you looked at weakly coupled Yang mills, but large N. Are you saying that entropies would obey this? There are some cases where we know that there are duals which are highly stringy. And maybe you look at the symmetric product orbifold, maybe there you can really compute some entropies at the orbifold point, not at the supergravity point. And you can show that these inequalities are a bit, And there you can really check the entropy. You can compute them independently. It would also answer Finn's question. What did you learn from them? Here's a check, independent check, where you weren't using area.
Okay, so I don't know if the entropies obey, if the vacuum of that theory obeys the inequalities or it doesn't. I have another example of a quantum field theory that we know and love where the vacuum does not obey it. But
it must, no, because we believe that there's a string dual, and that string dual, we believe that there is some. It obeys the criteria you said. There is some functional you can write down, which might or might not be the area that's associated to areas. So, whenever there's a string dual, even if it's not a geometric, gravity dual, it should work.
Let's talk more about this, because I don't have a.
Every time there's a string.
Even when you looked at the proof was stable. So as long as there's some function you can write down of the region, which might not be integral
of the boundary
area,
between the regions. So
but
it's all about the
minimum of
boundary.
some function. All these inequalities should hold. That was my understanding. Is that
correct? That's completely correct. Yeah. So it just has to be some function of. But I don't care what it is. It's a general statement about whenever it's. Well, let's. That's a. I'm just gonna. Extrinsic. That's okay. That's okay. It just has to be localizable on a codimension 1 surface. That's the only thing I care about. So.
execute on the replica trick, and it will localize to some. Okay, that's the argument.
I mean, it's not a very careful argument.
Okay, but maybe one can make it precise and then subject it to this test. And if it works for strongly curved geometry.
Very good. So thank you for that.
Okay, there are other questions?
Sorry, in the middle, you talked about the saturation of your inequality, like bipartite entanglement or perfect tensor. Can we realize such a saturation in the simplest setup of ADS-CFT? Because of ground state or just ADS black hole, but by fine-tuning the size of subsystem?
Yeah. So we basically want to construct something that looks like this tensor network. So so we would have we could without talking about the page curve and absorbing any Hawking quanta in the bath, but purely geometrically, just make a wormhole with arbitrarily many asymptotic regions. All of them are have equal minimal surfaces separating the boundary from the central region, except one which is like proportionally larger. That's definitely a geometry that exists. So that's what it is.
It is kind of one non-traversable one.
Yeah, so it's a non-traversable wormhole with sufficiently many.
For just pure ADS, is it possible? Some ground state global ADS and choosing some particular size of subsystem?
No, that for pure ADS that will not be possible, because the thing is that here the key thing is that I don't have any mutual informations up until this value of P prime, and whenever I try to define regions in a spatial way, there is always going to be some mutual information between them. So that's what. So in some sense, like the reason why it works that way is that you make those. I say that to do it, I have to have these separate boundaries. The separate boundaries are there precisely to kill off any potential mutual information here. That's why they're separate.
Okay, so we'll end. Oh, you have a question here.
Thanks for the talk. I have a question on some intuition. So you motivated the toric inequality and the projective plane inequality that they reduce to the same thing as the entropy inequalities. So can I think of this as like, is it a disjoint set of inequalities? Is it a bigger set? Is it a smaller set?
Well,
like, do you have any intuition for this question?
Well, I mean, they are a new. So I told you, we had this table, the impressive and disappointing table. Yeah. So I made the new inequalities. They are new entries in this table, and it's an infinite family. So it's an infinite addition with more and more regions going down the line. That's what role they play. It is also true that they cover many of the things in that table. And so this is P equals, this is like toric with M equals 3 and N equals 1. This is also toric with M equals 3, N equals 1, but relabeled in a funny way. This one is toric with M equals 3 and N equals 3. This one is the funny thing that lived on the hyperbolic, on the surface with Q cross caps. This one is the projective plane with M equals 3. And this one is the toric with M equals 3 and N equals 5. Okay, so really we have kind of, and this one is toric with M equals 5 and N equals 1. So as of this table, we unified all of them except for this one. But then when you go to these ones, there are many that don't live in that.
Okay, and can you elaborate a bit on, because you were able to prove the other things, so what's the complication in, let's say, the number 8 one? Or?
You mean here?
Yeah. Well,
they don't live on graphs like the graphs I just described for you.
Okay, so the method doesn't apply.
So so my method is not So I should avoid giving an impression that it unifies all there is to know about holographic entropy cone. This is emphatically not the case, because these inequalities make it clear that that's not the case. Now it could be the case in some there are a number of inequalities among these 1866, which are not of the form I just told you about, but they have an interesting property that their contraction maps are exactly the same as the contraction maps that prove those inequalities. We just, at some level in the contraction map, we just designate an extra term to be a boundary condition. After you do that, there is an extra thing you can do, which is that you can like sort of designate more rows to be boundary conditions and then set some regions to be empty. That will simplify. So there are a lot of things that once you know one inequality, you can generate many inequalities by some purely combinatorial things, yes? And I don't know how many of them are of that form, sort of originating from the ones that we found. It is conceivable that all of these inequalities are reductions of the ones that I just described for you. It's conceivable, I mean, but yeah, it's hard to say how likely it is.
Okay, but so it could be aspired to try to employ your method and modify it in some way that you can tackle all of these? Or do you think, like, because you were saying number 8 doesn't live on a graph structure, is it like a proven statement, or is it like just not found for now?
In its current form, it certainly doesn't live on a graph structure at all. But it could be that there was a graph structure, and then we designated some regions to be empty, and then suddenly the graph collapsed, and you got this inequality. So I'm just saying that there is there is some hope that the inequalities I found will have a lot of unifying power for even understanding these. But at present, we don't know that.
Okay, great, thank you.
So we'll end the morning session and we'll reconvene after lunch. Thank you.
Thank you. Thank you very much.